Bismillahirrahmanirrahim. Assalamu alaikum. Pakhair Raghlai. It's me, Atif Fakas, and today in this lecture of BS Physics Elementary Mechanics, we are going to discuss potential energy. Dear students, previously we discussed work energy theorem and we related work to the kinetic energy. Today we are going to express that work energy theorem in terms of potential energy. So we are going to relate work with the potential energy. Potential energy is a form of energy. It is the form of mechanical energy. And how can we define it? It is the energy that is associated to a system because of its configuration. If the system is such that it is a conservative system, by conservative system I mean that the forces that acts in that mechanical system are conservative forces, and we are going to define the conservative forces and differentiate it with non-conservative forces soon. But potential energy is the energy that is associated with the configuration of the system in which conservative forces act. And if a conservative force performs some work, it does work on an object, then the change in the potential energy of the object is delta U. We represent potential energy with U. So the delta U is then negative of that work done. So we discuss it soon why here is a negative sign. But if I want to express the same work energy principle in terms of potential energy, then it's like this. Here we are having a negative sign. So we would understand this with the help of some example. But the potential energy is, as I discussed, it is associated to the configuration of a system, and it is the energy that is associated to an object because of its position inside some conservative field, or because of the shape of the object, or it's because of the orientation of that mechanical system. We are going to understand the potential energy with the help of two different systems, and both of them are conservative systems. Conservative system is a system where total mechanical energy is conserved, where there are no losses in mechanical energy, where the total energy is in the form of the sum of kinetic and potential energy, and there is no other form of energy involved. So here we have two simple systems that can be considered conservative systems. One is the gravitational force, that is conservative force. The other is the elastic restoring spring force, that is also conservative force, and we are going to consider both the systems, and we would understand the potential energy from them. So first I consider a system that consists of two things. One is Earth having mass capital M, and the other is some small object, consider it a ball, having mass small m, and it is initially at the surface of Earth, which position is let's suppose position 1, and then if I change the configuration of this system, I change the distance between these two objects. One is Earth, the other is some object with mass m. If I change its position such that it is its distance from Earth change, then let's suppose I bring it here to this height. It covers some distance h. Now if I release this object from that height, it moves down. Initially When I release it, its kinetic energy is 0. But as I release it, it moves downward and its kinetic energy increases. So here from that kinetic energy comes. There must be some energy in that object that is stored in that object, which converts to the kinetic energy. And that stored energy in the object is its potential energy. And where from that potential energy comes, it is associated to the configuration of the system. I change the configuration of a system. I change the separation between these two objects. One is the large object, that is Earth, having mass capital M, and the other is small object having mass small m. And when I change the orientation of the system, the configuration of the system, when I raised this object to some height, I change the configuration of the system. I change the separation between them, and then I have stored some energy into that object, and that energy is called potential energy of the object. And this is not the only case where there is potential energy. We may take another example, and that example is the mass attached to spring. Here is mass m that is attached to some spring, and initially it is at rest here at its equilibrium position. I call it O, and if I disturb this system, if I disturb this equilibrium by exerting force in either direction, or in this direction or in that direction, what happens? The configuration of the system does change. How does it change? It changes because if I move this mass to some new position, and now I have changed it by amount x. Initially it had some position xi, and now it is having some other position xf. So once again, here too I have changed the configuration of the system, and there must be some energy in this object. And that energy is potential energy that is associated to this system because of its orientation. So the energy associated with an object because of its position inside some field, or because of the orientation of a system, is called its potential energy. Now, in both of these examples, you can see we are performing some work, and that work is stored in the objects in the form of their potential energies. We need to perform some work in order to change the orientation of a system. And if our work, to which we call work, if we exert force and that force does not change the configuration of the system, then no work is done. And that is because if energy of a system is not changed, no work is done. So, in previous case we discussed that if we exert force on an object that is having some velocity, that has some kinetic energy, and when we apply force on it, when we perform some work, its kinetic energy increase. But here, if we change the position of the object inside some potential field, inside some conservative field, its potential energy does change, and that change in the potential energy can be get back whenever we need it. If we release the object from that height, we can get the same potential energy back in the form of kinetic energy, and then if we want to use that kinetic energy for any purpose, we can do that. In case of when we strike a hammer, we store some potential energy in that hammer, and when we release it, that potential energy converts back to the kinetic energy, and then we can use that kinetic energy for either breaking something or inserting nail in some block or anything, we can use that kinetic energy. But why there is some negative sign in this expression? That is because the work that increases the potential energy of a system is always in the opposite direction, is always negative. The work that increases the potential energy of a system is negative, and the work that decreases the potential energy of a system is positive. How? If we raise this object above the ground and we exert some force on it, so the displacement is in upward direction, but the force on that object, because of the Earth's gravitation, the conservative force is weight, and that is downward. So we are moving against that system, we are moving against that restoring force, and that's why the force and the displacement are at 180 degree, the work is negative. And if we release that object, weight and the displacement are parallel to each other. But this time, the change in the potential energy would be negative. There will be decrease in the potential energy. When the work is positive, there is loss in the potential energy. When the work is negative, there is gain in the potential energy. And the same is in this example as well. If we exert force on this object in the direction opposite to the restoring force, and we stretch this spring, energy is stored in it, we discussed. Why? Because this force which we are exerting on it is taking the object away from that equilibrium position, but the restoring force all the time tries to pull it back, and the angle between the restoring force and the displacement is 180, work done is negative. If we move the mass attached to spring away from this origin, its potential energy increase, but that work is negative. And if we release it, it comes back towards the mean position. The restoring force and the displacement are parallel in this case, and then the potential energy decrease. So when work is positive in a conservative systems, when work is positive in the direction of restoring the system, the potential energy decrease. There is loss in the potential energy. And that loss in the potential energy may be termed as the gain in the kinetic energy. And once again we did discuss in previous lecture that kinetic gain in the kinetic energy is because of work. So positive work is equal to gain in kinetic energy, but negative work is equal to gain in potential energy. And we can conclude then work done particularly for conservative systems, work done is equal to gain in kinetic energy. We can write this as and delta is for the change, kinetic energy final minus kinetic energy initial. And the other thing, the potential energy, we can also write this expression in terms of potential energy is work done is equal to, if here is gain, it would be loss. We can write this as, so work is equal to minus delta U. The negative sign shows the loss, and this way I can write negative of potential energy final minus potential energy initial. And I can also write this so in both of these examples here below, we can see that if the work is done by that conservative system, remember this work is not done by some external agent, it is done by the conservative force. And if the work is done by the conservative force, that is equal to gain in the kinetic energy. And if that work is done by the conservative force, that is equal to loss in the potential energy. If conservative force does some work, that work decreases the kinetic potential energy, increases the kinetic energy. And we can take this example once again. If I release the object from certain height, what happens? Its potential energy decreases. Negative sign. Why? That is because gravitational force is performing work. Gravitational force is conservative force. It is doing some work. If I release this object from the extreme position, what happens? Restoring force does work. And that work decreases the potential energy. Potential energy is maximum when it is at extreme position. How about the kinetic energies? Here you see, if the gravitational force does work, it increases the kinetic energy of the object. The object gets faster and faster as it moves down. And in the same way, as this object approaches this position, equilibrium position, its kinetic energy increases. So the conclusion is, if the conservative force performs work, that work increases the kinetic energy, decreases the potential energy. But if work is done by some external agent against that conservative force, against the restoration of that system, that work increases the potential energy. So you can take many other examples, the examples of electric fields and Coulomb force, etc. are also of the same nature, but we discuss those things in electromagnetism. There is always some reference point in defining potential energies. That is necessary because we can define change in the potential energy. We can, this is change in the potential energy, this is not the absolute potential energy, which we will discuss in some other lecture. But here I am talking about the change in potential energy of mechanical. In mechanical system, we always discuss about the gain or loss of kinetic and mechanical energies. So let me remove this. Now, gravitational potential energy, that is then delta U is the negative work. Negative work in this case is I define work such that I consider the upward direction is y direction. This is ground level, and this is that height to which I raise this object of mass m. So I call this direction is y direction, and this is y initial, this is some y final, and work done can then be written as f dot dy. That is integrating the force over that path dy, and the intervals are y initial to y final. So what is force in this case? The force is mg. So if I write minus mg, and I can take it outside that summation, that integration, because m and g are kept constant. The height is not that much which can change g. So y initial to y final, and then I have only dy here. So what is the integration of 1? It is del u is minus mgy, but here are limits of integration, y initial and y final. And if I apply those limits, I see del u, so minus mg some y final minus the lower limit y initial, and this way I get, if I multiply this minus mg inside, I get mgy initial minus mgy final, and this is change in that potential energy. So if I assume that initial point to be at zero potential, then I can get an expression for this delta u is mg y final, and if I call this height is h, so this energy that is stored in that object is mgh, which you are familiar with. So this is the general expression for any two heights. Initially it has some potential energy, and then by applying some force we raise it, and its potential energy is changed. So this is how we calculate that change. And if we look at the another example, in this case of mass attached to spring, we can write this way: negative integration from some initial x to some final x, and this time f dx. Force is spring force, that is kx, so minus x initial to x final, and that is a kx times dx. And if I integrate this, what I get, minus k outside, and integrating x, we get x squared divided by 2 between two positions, x initial and x final. And then I can have this expression for the potential energy, that is half k x final square minus x initial square. So here we are having negative sign, and if I multiply that negative sign inside, then I have half k x initial square minus x final square. So from here we can have half kx square if we assume initially to be at equilibrium position, then we are having only half kx square, but this is the general expression for that potential energy. So in next lecture, inshallah, we will discuss the conservative forces and non-conservative forces in details. So take care of yourselves. Remember me in your prayers. Stay blessed. Assalamu alaikum.